So last week we talked about a specific function and then a general class of functions. This week we'll be doing the opposite. So let's start off with talking about general ad hoc number theoretic functions. So for several number theory problems, we'll be given a newly defined number theoretic function, and we'll have to extract some sort of answer from it. And with these functions, we typically won't have any prior knowledge about it. Unlike, say, the divisor counting function or the totient function, which we have formulas and properties for, these functions, since they're newly defined, we won't really know about their properties. So in order to replace this lack of prior knowledge, we're going to have to discover some properties of the function for ourselves. So in particular, for the next few examples, we'll be trying to study the function as much as we can. And then at the end, we can use our knowledge of the properties of the function to extract the answer fairly easily. So our first example will be this fairly wordy AIME problem. I'll give you a little time to parse this question and make sense of the variables and functions. So to begin, the main entity we'll be concerned with is this sequence X. We're given a recursion for it, and we want to find the smallest index for which X sub this index is this given integer, 2090. So we have this nice recursion, and then let's just quickly rewrite it so that we can solve for the next term of the sequence in terms of the previous term. So we have this expression. How might we interpret this expression? In particular, we're given a couple of functions in the problem statement, and we're mixing them in this way. So yes, we'll want to plug in the next few numbers, but to make it easier, well, we would want to understand what the function does or what the recursion means. So in particular, if we have an xn, then the factor of p sub xn at the top means that we find the smallest prime that doesn't go into xn and multiply it. And then the denominator tells us that we're going to want to divide out all primes less than it. So essentially, if we have a term of the sequence, to find the next term, we have to multiply by the smallest prime that doesn't divide this term, and then take out all the smaller primes. And in particular, we're hearing the word primes and multiplying and dividing a lot. So it suggests that it would be helpful to consider integers not based on their size, but based on their prime factorization. So considering the prime factorization of these terms will be useful. The sequence is a lot more natural when we consider prime factorizations rather than just plain size. So as suggested, let's work out the first few terms of the sequence. And I suggest working through the next few terms by yourself on paper, because I think it's a lot more instructive to see how the sequence behaves. So just to begin with, we know the first term of the sequence is 1, so the next term is 2. What would the next term be? We'll be walking through the first 8 terms or so. Any info on what x sub 2 is? Feel free to type in the chat. Did everybody get the recursion back there? Oops. I can go back to the recursion if anybody needs. So basically, to find the next term of the sequence, you want to multiply by the largest prime, the smallest prime that doesn't go into it, and then divide out all the smaller primes, which are going to go into it. So we had a spoiler, x sub 2 is 3. So essentially, x sub 1 is 2. What's the smallest prime that doesn't go into 2? That would be 3. So now we multiply by 3. And then we want to divide by all primes less than 3. So we multiply by 3 and divide by 2. That makes for next term of 3. So what would the next term of this sequence be? If we know that x sub 2 is 3, what would x sub 3 be? Yep, it would be 6. So to see this, the smallest prime that doesn't go into 3 is 2. So we multiply by 2, 6, and then we divide by all the primes that don't go that are less than 2, but there are none. So that would just be 6. And its prime factorization is 2 times 3. So how about x sub 4? Yep. So 5 is the smallest prime that doesn't go into 6. So we multiply by 5, and then we have to divide by all the primes less than 5, which are 2 and 3. So that ends up working out to 5. And then x sub 5. It would be 10 because the smallest prime that doesn't go into 5 is 2. So we multiply by 2, and we don't have to divide by anything. So that makes for 10. For the sake of time, I'll just talk through the last couple of terms we'll be working through. So we have 10. The smallest prime that doesn't go into 10 is 3. So we multiply by 3 and divide by all the primes less than 3. So multiply by 3 and divide by 2. That makes for 15. The smallest prime that doesn't go into 15 is 2. So multiply by 2, and we don't need to divide by anything. There are no primes less than 2. So it's 30. For the next term, the smallest prime that doesn't go into 30 is 7. So we're going to multiply by 7, and then divide by all the primes less than 7. So multiply it by 7, divide by 2, divide by 3, divide by 5, and that works out to just plain 7. So just a summary of what we did. We're going to want to find the smallest prime that doesn't appear in the prime factorization here. Then we're going to add it to the end of the prime factorization, or not to the end, just include it in the prime factorization, and then delete all smaller primes from it. That's basically what the sequence wants us to do. So does this remind anybody of some other operation that you might see in the sequence? Yeah, this is a lot like addition in binary. Whenever we add 1 to a number in binary, what we want to do is we find the first 0, change it to a 1, and then change everything to the right of it to a 0. And we're basically doing the exact same thing with the exponents in the prime factorization. So just for a bit more clarity, we'll be writing out the first few xi in this form. So when we consider the exponents of 2, 3, 5, and 7, this is what it looks like. And now you can see pretty clearly the structure of the sequence. 0, 0, 0, 1 is 1 in binary, 0, 0, 1, 0 is 2 in binary, 0, 0, 1, 1 is 3, and so on. So in summary, if we have the binary representation of n, then we already know what its prime factorization is going to be. So if we write it in binary, then we just have to take the appropriate primes and put the appropriate exponents. And we can, if you want, you can write a rigorous proof of this, but it's essentially fairly intuitive. Because in order to find the next term in the sequence, we're going to find the first 0 in the prime factorization, flip it to a 1, and then zero out everything to the right. And this is exactly the same as adding 1 in binary. You can see it with the sequence up here. Say we have a term. Well, we look at its prime factorization, find the first 0, change it to a 1, and then zero everything to the right of it. So in particular, this writing makes it extremely, this writing of the terms of the sequence makes it extremely clear that we're working with a binary sequence. So now that we know what the sequence looks like, we can extract the answer. So we have the prime factorization of 2090 being 2 times 5 times 11 times 19. So if we know that x sub t is 2090, how would we find how would we find t? I'll give you a nice way to read this prime factorization with all the missing primes appended. So how will we extract what t is from this prime factorization? Well, you see 1 0 0 1 0 1 0 1, and that tells you to read it in binary. And when we do that, we can get the final answer of 149. As a side note, the problem asks us to find the smallest value of t. But with this, with what we found about the sequence, we know that there's actually only one value of t, because every integer has a unique binary expression. That means each term of the sequence is different. So does anyone have any questions about this problem? If not, then I'll turn it over to Brian for the next problem, which I think is also from the AIME.
Okay, so here's the next problem. So we see that we have this remainder function, and then we take the max of the remainder function, and we want to sum it. Right, so I guess I'll give you guys a bit of time to think about it, and then we'll be going over it. Okay, so I guess our main goal here is to try to like understand what big F of n means, right? So what this tells us is that basically we just want to find which k is f of nk maximized, right? So, well, what does it, like, what do you need in order to have a large remainder when you divide by k, right? Well, basically the largest multiple of k less than n has to be a lot less than n, essentially, right? So, well, if we think about it, if there's a big gap from n to the largest multiple of k less than n, then that's also saying there's a small gap between n and the least multiple of k greater than n, right? So basically, what this means that we can do is we choose a k in a certain way, but this k, in order for it to be maximum, it has to satisfy a bunch of properties, right? In particular, it has to satisfy that if you were to increase k by a little bit, it has to if ki is if the least multiple of n that's greater than k is ki, but then it's k minus 1 is at most n. Well, what this means is that basically we can improve our remainder slightly so that we can increase the maximum. Right. So in particular, what this allows us to say is that if we rewrite our inequalities, k is of the form floor of n over I plus 1. So basically, we now just have to think about which I we want, right? Well, so first we remember the bound on k, right? K is at most n over 2, so I is at least 3, right? And now we do some computations of what f of n and k equals, right? Well, we sort of just, so the remainder is we have to subtract out I minus 1 copies of k because ik is going to be too big. And then so we sort of expand and then we get this. So essentially it's floor of n over I minus some small error term. That's at most I minus 1. Right, so essentially, so we remember that they told us that n only started out at 20. Right, so this helps us because this basically tells us that n over I is going to be the dominant term in this expression, right? And basically when n is at least 20, so if n over I is the dominant term, we want n over I to be as big as we can, right? And so this is essentially just minimizing I. And since I is at least 3, we just suppose why? So no, there's a missing parentheses here, but it's I minus 1 minus the quantity n mod I, right? And that's basically because we took n minus, so when we expanded this, we took n minus I floor of n over I, and then we added a copy of floor of n over I, and then there was that I minus 1 as well, right? Because basically if you take n minus I floor of n over I, that's equivalent to just taking the remainder of n mod I, which is where that term comes from. And then the I minus 1 just comes from the I minus 1 times 1. Right. So yeah, and now we want to think about so we claim that I equals 3 is the maximum value of this. And this is true because basically, so well, we get the idea of n over I is the big term. So if n over I is the big term, we want to make the big term bigger, which means that we want to make the denominator smaller, which means we want I to be smaller. And then n 20 is a pretty big number. And then so if we take the difference between n equals 3, n over 3 and n over 4, it's going to be sufficiently large to cover any difference that this second term will make. And so we just plug in I equals 3 now, and we got this. And so now we just need to calculate the sum of this from 20 to 100. And then this is just like a bunch of computations that you can probably do. It's like arithmetic sequence computation for the most part. And then so you compute it, you get your answer of 1512. So the final answer is 512. All right. Are there any questions on that? Oh, the previous slide. Okay. Here. Essentially, what we figured out here is n has to be of the form 4 of n over I. K has to be of the form 4 of n over I plus 1, or else K is not going to be optimal. Right. So, yeah. Do we have other questions? If not, I guess I'll pass it to Aditya.
Okay, so our next topic is the totient function. So we've discussed this a little bit more, but a little bit before, but we're going to discuss a couple more problems with it now. So for some review, the totient function is going to count the number of integers that from 1 to n that are relatively prime to n. And we can use this formula for computing it, given the prime factorization of n. And so we showed how to prove this in a previous lesson, but essentially you can use principle of inclusion exclusion and factor it to get this result for one method. And so the main result for the totient function is Euler's theorem. So if a and n are relatively prime, then a to the phi of n is 1 mod n. So this is just one property that the function has. In the resulting problems, we'll discuss a few other properties that it has. So the first problem we have is this identity here. So I'll give you a couple of minutes to think about it. Okay, so does anyone have any ideas for how we start this problem? Or any method that we could use to solve it? So here we have an identity in terms of n, right? So one method that, and it's supposed to hold for all positive integers n. So one method we might try is induction. So to try to use induction here, we want to, well, we can let f of n be this sum. We want to compute the difference between two consecutive terms, like f of n minus f of n minus 1. And if we find that difference in terms of n, then we can use induction with a base case to finish the problem. So let's look at this sum. Does anyone have any idea for what it's equal to? This difference f of n minus f of n minus 1. Okay, yeah, that's right. To see this, first, like, we would just subtract the two sums and write it in this form. So now we have a difference of floors in the parentheses. So what values does this difference of floors actually take? And so does so the question is to find what values that this difference of floors is. Yep. So whenever k is not a multiple of n, these two floors are equal, so then it's equal to 0. But when k divides n, then this difference is actually equal to 1. So we can ignore all of the terms when k doesn't divide n because that difference is 0. So then our resulting sum is just the sum of 5k where k divides n. And so someone has already said this in the chat, but this sum is equal to n. So let's try to prove this. So one way we can prove this is if we consider the fractions 1 over n, 2 over n, and so on all the way to n over n in reduced form. So how many of these fractions are going to have a denominator of k, where k divides n? So remember that if the fraction has a denominator of k when it's in simplest form, then the numerator of that fraction has to be relatively prime to k. So now does anyone have any idea for how many fractions have a denominator of k? Yeah, I think you meant 5k, but yeah. So like as I said, in order for this fraction to be in simplest form, the numerator has to be relatively prime with k. So that means since we know that there are 5k possible, there are 5k integers less than or equal to k that are relatively prime with k, that means that there's 5k possible values for that numerator. So there's 5k fractions with the denominator of k. And so the denominator has to divide n. So if we total up the number of fractions with a denominator, with each denominator, it's this sum over, it's the sum of 5k where k divides n. Because the set of denominators is precisely the integer, is precisely the set of divisors for n. But we note that we wrote exactly n fractions at the top here because you can just see from the numerators that there are n fractions here. So this means that this sum is also equal to n. So that proves the lemma. And so to conclude, we have that f of n minus f of n minus 1 is equal to n. And we can verify that the base case f of 1 is equal to 1. So you can prove, I won't write the whole proof again here, but the idea is we just use induction using this base case and with this difference of n here. And we can prove that f of n is 1/2 times n plus 1. So does anyone have any questions on this? All right, so if there's no questions, I guess William will take over for the last problem for today.
Yep, so this is the last question of the day. I'll give you guys a few moments to read it. And feel free to type any ideas in the chat. So does anybody have any ideas on how to begin? Well, first let's let the divisors of n be d1, d2, all the way to dk. So note that sigma of n is d1 plus d2 plus all the way to dk. So we only care about the interval between 1 and this quantity. And all we need to show is that there's at most n numbers relatively prime to n within this interval. Because that would mean that then the nth smallest positive integer is at least sigma n. No, we have to show that there's at most n minus 1 in the strict interval, and possibly the last one is sigma n. But yeah, technicality. So anyways, the problem with this expression is that d1 plus d2 plus all the way to dk is very difficult to work with for general n. So one way we can try to attack this is actually to, well, does anybody see how to attack this question, given that this sum itself is very awkward? Well, one thing we can do is just to split up the interval into k regions. So we're going to divide this interval, which has length d1 plus d2 all the way to dk, into k intervals. The first one's going to range from 1 to d1. The second one will range from d1 plus 1 to d1 plus d2. Then d1 plus d2 plus 1 all the way to d1 plus d2 plus d3, and so forth. So in this way, we split up our interval into k smaller intervals. So now let's just consider one of the intervals, which ranges between m and m plus di for some m. So how many numbers relatively prime to n are there in this interval? Actually, how many numbers are relatively prime to di in this interval, first of all? So note that whether or not a number is relatively prime to di only depends on the number modulo di, right? And since the range m through m plus di with the right end exclusive includes every single residue mod di, we can just assume that it's the range 1, 2, 3 all the way to di, because the set of residues is the same, so the number of relatively prime numbers will also be the same. So we can instead ask how many numbers are relatively prime to di between 1 through di, and then of course to answer just phi of di by the definition of phi. So since there are exactly phi of di numbers relatively prime to di in this range, and di goes into n, then this means that any number not relatively prime to di is also not going to be relatively prime to n. So at most, phi of di numbers in this range are relatively prime to n. So now once we have this, so we can just sum over all the intervals. So the first interval has phi of d1, then phi of d2, all the way to phi of dk. So we have at most sum from I equals 1 to k of phi of di numbers, which are relatively prime to n in this range. And by what Aditya said earlier, this is just equal to n, since we sum over all divisors of n. So this tells us that there's at most n divisors in this, there's at most n numbers relatively prime to n in this range. So this basically solves the inequality. Of course, there's some edge cases, but we'll get to those. So first of all, let's consider, so now we're going to claim that equality is only going to hold when n is a prime power. So suppose that n is equal to p to the alpha. What we want to show is that the nth smallest number relatively prime to p to the alpha is equal to the sum of the divisors. So can anybody tell me what the sum of the divisors of n is? N is p to the alpha. So since n is a prime power, yeah, basically it's factors are going to be 1, p squared all the way to p to the alpha. So that means that its divisor sum is going to be p to the alpha plus 1 minus 1 over p minus 1. So sigma n is equal to 1 plus p plus all the way to p to the alpha. This is a finite geometric series. So we just use the formula p to the alpha plus 1 minus 1 over p minus 1. So now for the latter, we want to find the nth smallest number relatively prime with it. Well, note that there are p minus 1 times m numbers relatively prime to p to the alpha, which are less than pm for any m. And this is because a number is relatively prime to p to the alpha if and only if it's relatively prime to p, since p is the only prime factor of p to the alpha. So the number of numbers less than pm relatively prime to p to the alpha are just those which are not divisible by p, which of course accounts for p minus 1 times m of them. So now we want to find the p to the alpha smallest number which isn't divisible by p. Well, there are p to the alpha minus 1 numbers relatively prime to n, which are less than p to the alpha plus 1 minus p times p minus 1. Since we get p to the alpha minus 1 when we multiply by p minus 1 over p. So we just need one more number which is not divisible by p. So the nth smallest number relatively prime with p, which equivalently is relatively prime with p to the alpha, is p to the alpha plus 1 minus p over p minus 1, and then add an extra 1. And we get that this is just equal to sigma n. So we prove it for, so we have proved the statement for prime powers. So now suppose that n is not a prime power. Then suppose we have distinct primes p and q such that pq divides n. And let's assume that p is less than q. So recall that when we made our inequalities, what we did was we split it into the first interval has d1, the second interval has d2. We never defined the order of the d's. So let's just suppose that the first interval has size q. So q is equal to d1. But since p is less than q, this means that in this interval, there's actually a multiple of p. And this multiple of p is, of course, relatively prime with q. So in this interval, there's going to be phi of q numbers which are relatively prime to q, which is what we want. But there's at most phi of q minus 1 numbers relatively prime to n, since we have to subtract out the multiple of p. So this means that the inequality is not strict in this interval. And that's enough to show it that the inequality is not strict in general. Because now the sum of the number, the number of relatively prime numbers with n over all intervals is going to be sum of phi of d2 plus phi of d3 all the way to phi of dk, and then plus phi of d1 minus 1, which is at most n minus 1. So equality cannot hold. And hence our answer is just the prime powers. So that finishes the question. So are there any questions? Yeah, so here was the last slide. Sorry that the screen share ended. Okay, well, if there are no questions, this was the last question of the day, so that's it for this week's class.